The final part to understanding the quantum model of the atom is the quantum numbers. Okay, so now we are going to try and establish where these electrons exist. So we've kind of understood about the shell numbers, okay, that we know that there is shells and the electrons are in shells, they travel in waves and all of that. But now we're going to talk about where those electrons really exist. How many can there be? What are those wave functions that we talk about? All of that is going to be given in this presentation. Now, in this portion, things can get a little confusing. Okay, so you may want to sit down with a notebook. Mine is all presented here, but you really want to take good notes over here so you don't get confused. Because when you talk about quantum numbers, the numbers can be a bit much, okay? And then you're like, I think we just talked about this. What are we talking about now? I'm completely lost, okay? So in order to eliminate those confusions, sit with notes, write something down so you will know where you are, okay, with all of this. Okay, so first of all, there are going to be 4 quantum numbers that we talk about, all right? Principal quantum number, angular momentum quantum number, magnetic quantum number, and finally the magnetic spin or the electron spin, okay? Each of these have their own designated letters, so N, L, ML, and then MS, okay? The first 3 are very critical in establishing the wave function. Where is that electron and how is it moving? What kind of wave it's in and all those kind of things, okay? The last one is to pinpoint a little bit deeper into the electron. The way I look at the quantum numbers, okay, is that when we are trying to say where an electron exists, it's almost like we are trying to give the address of an electron. So when I talk about an electron, you know exactly which electron I'm talking about, okay? Which means this is kind of the address, which address, like a home address, okay? And not just like a, with the city and there's the road number and the house number, but this is the room number also that we're talking about, okay? So we are going from the biggest point to the smallest, okay, and handing the letter that we wrote for that one electron to that one electron, okay? That is how specific the quantum numbers are. So it can get a little confusing because it's numbers, but still, I'll do my best and you also do your best in taking notes. So let's talk about the principal quantum number. I think like this is the easiest one, okay, to handle with. Remember how we're going to go, okay? So we have these 4 quantum numbers. We're always going to start with the principal quantum number. That's the first one, then the second and third and the fourth, okay? So that's how these quantum numbers go, which means that the principal quantum number is always going to be the first one we talk about. The principal quantum number is given by n, and n is the shell number or the orbit. So me, I have the habit of kind of going back and forth with the orbit and the shell. So I just want to write both of them. So if you hear me doing that, it's the same thing, okay? So which means that these lines, the blue lines that I have, the curved lines, these are the shells, okay, or the orbits, okay? So this is where the electrons exist. So here the red one here is the nucleus, and when you look at the red thing, that should focus you on the nucleus. And then we have shell numbers. Shell numbers can go from n is equal to 1 to 2 to 3, 4. You can go up 7, 8, 9, 10. You can have as many shell numbers as we need. I have written only 4 because, I don't need to make a whole big diagram for anything. I just need to explain how these quantum numbers are working, okay, for us. Okay, so first of all, this n number can only have 1, 2, 3, 4, and so on. It cannot be a fraction, it cannot be a 0, it cannot be a negative number. Okay, so only positive numbers, only whole numbers. That's it. The larger the n value, the greater the distance from the nucleus, first of all. So n is equal to 2 is farther away than n number 1. Okay, so as the number gets larger, the distance gets larger. As the n number gets larger, the energy is also increasing. Okay, so I've written that here as well. So energy is increasing. I'm going to be talking about the energy also, okay, as we go on, because that was the basis for everything, right? The line spectrum. So as you go farther away, the energy is also increasing, the size is also increasing. There is one thing that I want to show over here, which I will not mention again, okay? But I just want to kind of mention to you, it's a disclaimer to you right now. The distance between these shells is not equal, okay? So these shells, they are closer than they're farther. We know from the structure of atom is that there's a lot of empty space here, okay? Remember, the bulk of the mass is in the nucleus. So there's a lot of empty space going on over here. And so there's a lot of space here, okay? And nothing exists over here because the line spectrum has established that electrons will always be only in a very specific location. So it's like the Earth. The Earth is going around, around the sun in a very specific path. And that's the path, okay, that we're talking about here. So keep that in mind, okay, as we are going through all of this. If you don't write the equidistant, I'm fine with it, okay? And if I don't write it, I hope you are fine with it. But these distances are not equal, okay? For me, it's going to be the same structure from now on because I'm going to work on this same diagram as we go on. So the principal quantum number was the first number. Okay, remember we have 4 quantum numbers. So this is kind of like the city, and this is the first number that you write. Now we are going to go inside the shell. Okay, remember we're going like from city to road number to house number to the room number. That's how we are going. Second number then is the angular quantum number. The angular momentum quantum number or angular number, which is called the L number. So how do you figure out L? L is n minus 1. I know there is a lot of stuff on this slide, but just stay with me, okay? So L is equal to n minus 1, which means it can be 0. Now, it's not just n minus 1. But it is all the numbers between that also. All right, so let's calculate some numbers. When n is equal to 1, then L is equal to 1 minus 1, which is 0. When n is equal to 2, then L is equal to 2 minus 1. So it can be a 0 or a 1. So any number from 1 to 0. Okay, so n minus 1 to all the way to 0. So when n is equal to 3, then L can be 3 minus 1. So 0, 1, and 2. These are the possible numbers, okay, in there. So I've shown that to you over here, okay, as we are going to keep going on learning about the quantum numbers, this will start getting crowded. So when n is equal to 1, L is equal to 0. When n is equal to 2, there are 2 possibilities for L, 0 and 1. When n is equal to 3, L is 0, 1, or 2. Okay, these 3 are all possible values. This also means these are all allowed values. Okay, which means what is not allowed? Minus 1 is not allowed. When n is equal to 3, 3 is not allowed because it's supposed to be n minus 1. So when n is equal to 3, L cannot be 3. Okay, so do you see what I mean now? Okay, by allowed numbers and then not allowed numbers, you don't see any fractions here either. Okay, so when n is equal to 4, and I'm going only up to n is equal to 4 because, I mean, we can go on, but we only have so much room. So when n is equal to 4, then L has the possible numbers of 0, 1, 2, 3. Now, does it have all these 4? That depends on the number of electrons we are working with. Okay, so, and remember, that's the point. We're trying to figure out where these electrons really are. Okay, so we have hydrogen with 1 electron and we have xenon with 54 electrons. So where those electrons exist is really where we are going, okay, for right now. Okay, so I need you to understand this portion also a little bit. So what these numbers mean for us, okay, is that when shell is equal to 1, there's only one space, 0. That's it. When n is equal to 2, there are 2 spaces, okay, for electrons to exist. These are called subshells also. You can also call them orbitals. Okay, so subshells or orbitals. Both of them are fine because remember we are going from orbit to orbital, shell to subshell. Okay, so in n is equal to 3, there are 3 spaces for electrons to exist. And now there are 4 spaces for electrons to exist. Now you might think, okay, so when I'm talking about 1, what am I talking about? Am I talking about this one or am I talking about this one? So with the numbers, things can get a little bit confusing. So for that reason and for other reasons also, the L numbers have alphabets, okay, to go with them. So when L is equal to 0, it's called the S subshell. When L is equal to 1, it's the P subshell. When L is equal to 2, it's D, and L is equal to 3 is F. What does that mean? When n is equal to 1 and L is equal to 0, it means this is the S subshell. When n is equal to 2, then L over here is 0 or 1, which means n is equal to 2 can have S or P and P or P. When n is equal to 3, then L is 0, 1, 2, which means that when n is equal to 3, there are 3 orbitals here. When n is equal to 3, you have S, P, and D. When n is equal to 4, you have 4 subshells present here, and the 4 subshells are S, P, D, and F. Okay, so this is where the electrons are allowed to be in. There is no half. There is no 1.5. Okay, nothing like that. So this is where the electrons exist now. So we went from shell number to subshell. Now, moving on. Now we're getting into a little bit deeper into the subshell. Okay, so we had the L number. Now we're going to talk about the magnetic quantum number, which is defined by L. Okay, so remember we went from N to L. We derived L from N, and now we are deriving ML from L number. Okay, so depending on what L is, ML can be minus L to 0 to plus 1. So what does this mean? When L is equal to 0, then ML is only 0 because 0 gives only 0. When L is equal to 1, then ML can be minus 1, 0, or plus 1, which means there are 3 numbers possible for ML when L is equal to 1. When L is equal to 2, then ML can be all the way from minus 2 to plus 2. So which means there are 5 numbers possible. When L is equal to 3, ML goes all the way from plus 3 to minus 3 because we have to include all the numbers. What does all of this mean? What we are talking about is the orientation in which these orbitals exist. Okay, so we had the shell number n, then we had the L number. Okay, now we have the orbital, right? The S, P, D, and F. So now what we are saying is that S, L is equal to 0, S exists in what kind of an orientation? The orientation is spherical. And there's only one orientation possible because there is only one number for ML. And that orientation is spherical. This is what it looks like. This is a cut kind of a thing just to show you what inside is. But otherwise, the S orbital will look like this. Now, when L is equal to 1, that is a p orbital. So I've written those over here also for you. Okay, so the p orbital has 3 orientations: minus 1, 0, plus 1. There are 3 orientations. Now, when L is equal to 1, that orientation or that shape is called a dumbbell shape. This is what the dumbbell shape would look like, just like your weights, the dumbbell. That dumbbell is going in 3 different orientations, X, Y, and Z. Okay, which one is which? It doesn't matter. Now, when L is equal to 2, there are 5 orientations. Here are the 5 orientations. You can see that the shapes are getting more complex. This was so simple. This was getting more complex. D is getting more complex. And then when you get to L is equal to 3, which is F, which has 7 orientations, look at how complex this is. Okay, very complex now. So simple to complex to more. One orientation, three orientations, five orientations, and then seven orientations. Okay. So first of all, and I need to explain this also, I forgot in the previous slide, so I'm just going to talk about this here because this is kind of a little bit of a weird thing sometimes. Okay, so that's why I kind of like debate whether I should say it or not, but still. As you go from SPDF, the energy increases. Okay, so when L is equal to 0, that's low energy, L is equal to 1 is higher energy, L is equal to 2 is higher energy. So this is how the energy is increasing, okay, for the L numbers. The ML numbers, on the other hand, they are what we call degenerate. Degenerate meaning they're all the same energy. Okay, so I'm going to write that over here for you, but they all have exactly the same energy. There is no difference. Okay, so if you have one orientation, well, that's going to have the same energy. Three will have the same, this will have the same, all of these ones will have the same energy. Okay, so that's one of the things that we need to understand. The other thing that I have to add on here, which I did not, so I'm going to write it here for you right now, but each of these orientations can have 2 electrons. So this is 2 electrons. Each orientation here can have 2 electrons, 2 here, 2 here, 2 here. So that means this is a total of 6 electrons. So again, 2, 2, 2, 2, and 2. So that's a total of 10 electrons. So you can see how we are housing electrons now. Okay, we went from the shell number to, this was the N number, so then we went to the L number. From the L number we went on to even deeper orientation. Okay, so if N is equal to 2, we went from S and P, right? This was only S orientation. This is S orientation, this is P orientation. S can have 2 electrons and P can have 6 electrons now. So which means we're talking about shell number 2 that can have up to 8 electrons. Okay, so hopefully you see what we mean by this now. So then when you get to F, which has 7 orientations, that can have up to 14 electrons. So we are learning how these electrons are actually housed within each of these orbitals. Okay, so all of these orientations, all of these numbers, that's what they're telling us. And again, each orientation can have 2 electrons and they're all equal in energy. Now that word for it, it's called degenerate. Okay, so this is the magnetic quantum number, okay, ML number. We are at the third number now, okay, so which means we have only one more number to talk about, okay, so, oh, here I have more stuff, okay, I thought I only had one slide. I don't know why I thought that, but anyhow, so here it is. So there are 2 electrons in each orientation. So here I've given you all the orientations again. Here are the orientations, the number of electrons, okay, that we have for all of these different orientations. So this is how we go with all of this ML numbers, because now we are really getting into the house. Okay, we'd say, so we did the city, we did the house, and now we're getting inside the house, okay, into the different orientations. This is what it should look like. Okay, so shell number 1, shell number 1. L is equal to N minus 1, which is equal to 0, which is S. ML is 0 for that. Total number of electrons, 2. For shell number 2, L is N minus 1, so it could be S, it could be 0 and 1, which is S and P. So ML numbers possible. For 0, it is 0. For 1, it is minus 1 to plus 1. So which means 2 electrons here and 6 electrons here, a total of 8 electrons. What does it tell you? It means that shell number 1 can have 2 electrons. Shell number 2 can have 8 electrons. Shell number 3 can have a total of 18 electrons. How so? 2 from here, 3 from here, and 5 from here. Okay, 2, 6, and then 10. Because ML number has 1 orientation, 3 orientations, and 5 orientations. Each of those orientations can have 2 electrons. So this is shell number 4, and then you can see what I'm meaning by this then. Okay, so this is a total of 32 electrons for shell number 4. So that is how it exists. Now, if you're wondering how can I figure out how many electrons exist in shell number 7, you can, and the formula for that is 2n square. Okay, so just fill in the shell number. So if you want to find out for the 7th shell, so 2 times 7 square, you can do the calculation, okay, and figure out how many electrons there are. So 2n square is the formula for that. Okay, so now for the last number, which is the ms number. Okay, the ms number is what's called the magnetic spin number. The magnetic spin number has only 2 values, +½ and a -½. And this has to do with how the electron is spinning. So it turns out that electrons are moving in waves. Yeah, let me make you dizzy again. So here they're moving in waves. But not only are they moving in waves, they're moving within themselves too. So just like the Earth, it's moving around the sun, but it is also moving on its own axis. So if it moves on its own axis, what does it do? We have the day and the night, of course, because of that, but we also have a north and a south. We have magnetic poles because of that. So just like that, electrons are also in motion, and then they also have those kind of orientations where they are facing one way or another. So what we are saying is that the electrons can spin in one direction only. Okay, so which means that if you have 2 electrons in one orientation, which is what we said we have. So for example, in S, we said that there are 2 electrons. So S is supposed to be spherical. And let's say an electron can be written like this as an arrow. So if it's an arrow, then we'll say that those 2 electrons, they exist in opposite spin. Now, which one is +½ and which one is -½ we don't know. And I'm not saying that we don't care, but really we don't care, okay, because it doesn't matter. All right, you can designate whichever one as whichever one, so long they are in opposite spin. Okay, so can they exist in this kind of a spin? They can. It will be very high energy though. Okay, so this is the preferred spin, and this is called the magnetic spin. So when I said to you that we'll be delivering the whatever love letter we wrote to our electron, we're going to deliver it to the particular electron. There it is. There is the final number, okay, that we have. So each electron has its own address, and all these quantum numbers, what they do is they provide us the address, okay, for that electron. So that's what quantum numbers really are, okay? And the last one is just about spinning and existing in that one orbital. That is how quantum numbers work. Okay, so I think we can move on from here because there's really not much going on. By the way, the spin number, the electron spin number, this is also called magnetic spin number. It actually gives magnetic properties to the electron. Okay, so just like Earth has magnetic properties, electrons also, because of this spinning, they have magnetic properties. So here are all your quantum numbers. Here is a summary of everything. So the principal, angular, magnetic, and quantum electron spin. And here are the alphabets. I've tried to make it color coded for you so that, you know, it's not that it's easier. You're not going to remember the color, but still, okay, it's easy for you to differentiate then. And then what it tells you, how to calculate it, and what any other information. Okay, so this is kind of just a summary of everything that we have talked about. These are the allowed numbers. So when we say something is allowed, okay, that means that in some cases, some numbers are not allowed. So for example, when n is equal to 1, L can only be 0 because L is n minus 1. So L can never be 1 when n is equal to 1. So that number is not allowed, okay, for us. And remember, when L is equal to 1, that's actually a p orbital. So which means that shell number 1 can never have a p orbital. It's not possible, okay? So that's kind of what we figure out with allowed numbers and the not allowed numbers. So my questions to you are kind of targeted like that, okay? That we're talking about these set of numbers. Are these numbers allowed or not? okay? Or here's an electron. Is it allowed to be here or not? Okay, something like that. That's kind of the questions you will get. So here is again some things, if you want to just read it again, because as I said, sometimes these quantum numbers can get a little confusing. So here, if you want to read another version of it, you can. I don't want to read everything, so you can read it yourself. Yeah, this is what I like to do, problems. Okay, so which of the following numbers are possible? Okay, this is like a typical question that you will get. So the first one is n is equal to 3, L is equal to 4, ML is equal to 0, and MS is half. So is that possible? So it's definitely not possible, because when n is equal to 3, L is not possible. L is equal to 4 is not possible, because L is supposed to be n minus 1. Let's look at the next one. So if n is equal to 3, then L is equal to 2, L is equal to 0, and MS is minus half. Is this possible? Looks okay to me. Does not seem anything wrong with it. Now, remember, ML can be anything, right? Because if L is equal to 2, ML could be anywhere from +2 to -2. Okay, so 0 is perfectly allowed. It doesn't have to be -2 or +2. Oh, the third one, I didn't even talk about this. Okay, so n is equal to 2, L is equal to 0, ML is equal to 0, and MS is equal to -3/2. -3/2, forget that. That's not happening. So MS can only be these two numbers. Okay, so this is not going to be allowed in any way. Okay, so then n is equal to 5, L is equal to 4, ML is equal to -3, and then MS is plus half. Yeah, that kind of looks fine to me. Yeah. Just a little piece of advice, as you're doing these kind of questions, always start from n is equal to whatever. Okay, look at the n number first, then look at the L number, then look at the ML number. Okay, and lastly, you look at this number. I mean, unless you see something like this is like totally out of, it's not possible. But other than that, if these were all plus half and minus half, please go step by step. Okay, start with N, go to L, go to ML, and then go to MS. Okay, that's the order you should be going in order to figure out the order of correctness, okay, or permissions. Okay. So in this case, what are we doing? What are the quantum numbers of the following electrons? So when you have a 3p, 3d, 6s electron going on over there, 6s electron. So then the 3p, it means that in the case of 3p, the 3 here is the shell number, okay, that we are given. So 3 is the n number, okay? So we're writing the quantum numbers, okay, for this one. So 3 is the shell number. P, you need to know whether that is 0, 1, 2, 3, or 4, what that is. And that's the ML number, remember that. Okay, so that's how it goes. So let's look at the first one. So for A, shell number is 3 because that's a 3 given to you. L has to be 1 because that's a P thing. Okay, so P is L is equal to 1. ML can be anything now. ML can be -1, +1, or 0. MS can also be plus half or minus half. The main thing here was L is equal to 1. That's the main thing over here. Okay, so I've given you all the different possibilities. Okay, that could be correct. So you can see that we have to stick with these two numbers. The rest could be anything, okay, in there. So similarly with the 5d electrons, we really have to pay attention to the n number and the L number. Okay, then the ML comes from the L number. So for 5d, you have shell number 5. L has to be 2 for that. Okay. ML can be anything. ML can be all the way from +2 to -3. It can't be -3 because L is equal to 2. So you have to derive your ML from L number. Okay, so don't just randomly pick any number. It's coming from the L number, but it can be anything between +2 to -2. Okay, and again, MS can be either of these two. So you see where I'm going with this, right? So 6s would be then N is equal to 6, and then the L number will be 0 for S. Okay, and so then you're limited to ML, because ML here can only be 0 because L is 0. That's it. Okay, so you can see how systematically you can write all these quantum numbers. Okay, it's kind of a language on its own, and you can see how we are designating the address of the electron. Okay, so yeah, I mean, the electron can be here, here, or here. Okay, but at least you're close to where it is supposed to be. So final thoughts on quantum numbers. Yeah, the title of the slide is that this actually all tells us where the electrons are. Okay, we cannot just randomly assign electrons to anywhere. Okay, we have to fill them in a proper way. There are certain places where electrons go, so that's what we have to do. Okay, for the quantum numbers, for the electrons. Okay, they go in a very specific place. We're going to learn more, of course, about filling electrons. Right now we're just learning about where they go. We're not talking about how we fill them. Okay, we're just talking about, okay, this is the space where they're allowed to be in. Okay, so the final things that I have here for you is just some shapes of the orbitals. So here you can see that we have the different s orbitals. Again, as the shell number increases, the orbital size also increases. Okay, the lines here, they tell us a little bit about the wave function. Okay, remember we talked about wave function, the psi positive, psi negative, and a node. So where electrons can exist and where they don't exist. So the positive and the negative side, those are kind of given here. The nodes are kind of the borders. Okay, so electrons do not exist in those borders. Excuse me, that's how it goes. And then here we go. Here are the p and the d orbitals. Again, as the shell number increases, the size of the orbitals also increases. Now in the p, it's kind of easier to see where the node is. You can see where the node is right in the middle. So electrons can be in this red bubble or the blue one, but not in the middle here. That's the node. Okay, there are 3 orientations for p. So these are the 3 orientations in the different shells. They are the same p orbitals. They're just in different sizes. Okay, that's all it is. Same thing with the d orbitals. D orbital has 5 orientations. So these are the 5 orientations. As far as learning the orientations is concerned, okay, I would recommend that you learn about the s and the p. The D and the F you learn a little bit more when you get to inorganic chemistry, because that's when you start getting into D and F orbitals. At this point, I would have you just focus on the s orbital and p orbitals for my class, at least. Okay, so you don't have to memorize all of these shapes. Eventually you may have to if you pursue chemistry, but not for right now. Okay, because all of these orientations, they have very specific calculations, and this is very theoretical. And in some cases, these orbitals have also been seen in instrumentation, so these do exist. And then F orbitals are really pretty, and they have such a variety of shapes. Okay, really complicated. So just enjoy the picture. And so this is what a 4th shell would look like, with 32 electrons, where you have the s orbital, the p orbital, the d orbitals, and it's pretty crowded space with 32 electrons. Remember, each orientation can have 2 electrons, right? So, p has 6 electrons and so on and so forth. So pretty nice looking atom. What is 32? 32 is germanium, so that's germanium. And that's it. Okay, so there's lots to do, but it's not super hard, I think. Okay.